Good day, everyone. This laboratory report was performed by fifth-year chemical engineering students, namely Ms. Camila Datu, Ms. Demi Alavencione, Mr. Rojan Galicio, Ms. Melissa Lanipao, and Ms. Eliza Tolentino. The students mentioned were able to acquire the intended learning outcomes for this experiment. The experiment was performed to investigate and determine the flow properties of deposited layers comprising different granular materials and sizes.
For our introduction, the chemical industry is considerably important to economies around the world, playing a critical role in processes ranging from the production of clean drinking water to the manufacture of pharmaceutical products. Chemical engineers are faced with the challenge of ensuring profitability of a rapidly growing and evolving market. Packed bed reactors are one of the most common reactors used in the chemical industry due to their high conversion rate per catalyst weight compared to the other catalytic reactors. A typical packed bed is a cylindrical column that is filled with suitable packing materials. The liquid is distributed as uniformly as possible at the top of the column and flows downward, wetting the packing material. A gas is admitted at the bottom and flows upward, contacting the liquid in a countercurrent fashion. Flow through a packed bed can be regarded as fluid flow past some number of submerged objects. In this case, the objects are uniformly spherical particles of diameter. When there is no flow through packed bed, the net gravitational force acts downward. When flow begins upward, friction forces act upward and counterbalance the net gravitational force. For a high enough fluid velocity, the friction force is large enough to lift the particles. This represents the onset of fluidization. These are the materials that we use in flow-through packed bed experiments. We have water and kerosene as the process fluid and mercury as the manometric fluid. These are the materials that we use in flow-through packed bed experiments. First, set the selected length of packed bed, nominal diameter, and packing material. Second, set process fluid to water and manometric fluid to mercury. Third, click the green button to run the experiment. Fourth, set the required flow rate ratometer with increasing value until it reaches the maximum flow rate. Fifth, record H1 and H2 of the manometric fluid. Sixth, repeat the process at a different length of packed bed 0.5, 1, 1.5, and 2, different nominal diameter 0.25, 0.50, 1, 1.50, 2.50, and different packing material 25 mm rusting ring, 25 mm burl saddle, 13 mm burl saddle, and glass beads of 4 mm size. And lastly, repeat the experiment using kerosene as the process fluid.
For the experimental setup, the virtual laboratory features all required fittings and different pipe diameters. The laboratory apparatus is consisted of an inlet tank and pipes mounted on a stand that are connected to the inlet tank. Each pipe is provided a suitable distance apart. A regulating valve is provided at the downstream side on each pipe to regulate the flow. A U-tube manometer containing mercury is connected between two pressure tappings. This is the virtual laboratory from NITK Chemical that we use in order to execute the experiment. As you can see, there are several parts of this equipment on the simulation. First, the pump, bypass valve, main bulb, float, rotameter, YouTube manometer, and all the fittings given in the pipings.
This experiment enabled us to quantitatively determine and report the effect of superficial mass velocity on pressure drop across the packed bed with liquid flow, and the effect of modified Reynolds number on modified friction factor. The results were achieved by using an HG manometer set up in a virtual laboratory. The procedure was performed simultaneously with given parameters such as the packing material used were 25mm Rashig ring, 25mm Burl Seidel, 13mm Burl Seidel, glass beads of 4mm size. The nominal diameter of the packed bed used were that of 0.25, 0.5, 1.0, 1.5, and 2.5 inches. Lastly, the length used are 0.5, 1.0, 1.5, and 2 meters. The experiment was successfully performed by observing the change in heights by setting 4 different flow rates for both water and kerosene by using the rotameter provided. The process was observed carefully, and after such time, the heights were noted down. After collecting the raw data, we have calculated the porosity of the bed, the area and the volume of the bed, the dP, the volumetric flow rate, mass flow rate, superficial mass velocity, HW, delta P, the equation involving Reynolds number, and the Ergens equation. Then we verified for both water and kerosene as process fluids. After determining such values, we have prepared the log-log graph of delta P versus superficial mass velocity and the Ergens equation versus 1 over Reynolds number. These calculations let us acquire intended learning of this experiment that includes the determination of deposited layers comprising different granular materials and sizes. Another one is to analyze the flow properties of deposited layers of different heights. Analytical results indicated that the friction factor at a given Reynolds number in the turbulent region depends on the ratio of average roughness to the diameter of the pipe. With increasing Reynolds number, the thickness of the sublayer decreases. The higher the roughness of the pipe, the lower the value of Reynolds number, at which the curve of friction factor versus Reynolds number branches off from the smooth pipe. On the other hand, the rough pipe flow's pressure drop is approximately proportional to the square of the average velocity of flow. Thus, friction factor becomes independent of Reynolds number in these situations. Flow rate increases as the pressure drops across the bed since Reynolds number is directly proportional to the flow rate. The trend in the pressure drop with Ergens equation is shown in the log-log chart, where it was seen that the pressure reduces as Reynolds number increases. This is the result of reduced pressure in turbulent flow, which is different from that of the laminar flow, since laminar flow has a smaller Reynolds number.
These are the raw data that we have gathered in order to get the desired objectives for this experiment.
Next, we need to know the potential hazards that we encounter if we utilize this experiment in the real laboratory. First, the exposure to mercury. As we know, mercury exists in various forms such as elemental, inorganic, and inorganic. These forms of mercury differ in the degree of toxicity and their effects on the nervous, digestive, and immune system, and on lungs, kidneys, skin, and eyes. Next, for pump, the risk from a pump in the pipe blowing and causing injury to person can happen. Appropriate control measures include well-maintained, high-pressure clamps and securely anchored safety chain fitted to the instrumentation cap are needed. Next, for waste disposal. For proper disposal of mercury, mercury is considered as hazardous waste. When products containing mercury are placed in the trash, the mercury doesn't disappear. It finds its way into the environment. That's why mercury-containing products cannot be disposed of with regular trash or poured down the drain. Mercury products and compounds must be recycled or managed as hazardous waste. This is the steps for proper disposal of mercury. First, put on gloves, all clothing, all shoes, and remove jewelry. Second, transfer mercury with an eyedropper. Next, seal and label bags or containers that contain mercury waste. And finally, find a location to dispose of mercury waste. Thank you for listening.